Semigroups and their representations, Lecture 19, Schur-Weyl dualities. Let us start with the setup for the classical Schur-Weyl duality. Let n and k be two positive integers. Consider the vector space C to the power n, so that n-dimensional vector space over the complex numbers, and let us denote the standard n-dimensional vector space by V. Consider also the tensor power V to the tensor power k. So V tensor V tensor V, k factors. We can view V as a natural module over the group of all invertible n times n matrices. So invertible n times n matrices act on vectors with n coordinates. Then V to the tensor power k is also a module over this group via the diagonal action. So an element A in our group acts on the tensor V1, tensor V2, tensor and so on by acting on each component individually. So the outcome is A applied to V1, tensor A applied to V2, tensor and so on. Also consider the symmetric group Sk. Then V to the tensor power k is also an Sk module, where now Sk acts on the indices of our tensors. So applying an element sigma in Sk to V1 tensor, V2 tensor and so on, we get V with the index sigma of 1, tensor V with the index sigma of 2 and so on. So elements of Sk act on tensors by permuting the factors. Now we can formulate the classical Schur-Weyl duality. So theorem, we have the following. Claim number 1. The actions of GL and C and Sk on V to the tensor power k commute. Claim 2. The image of the group algebra of GL and C in the space of all linear operators on V to the tensor power k coincides with the centralizer of the Sk action. Claim 3. The image of the group algebra of Sk in the algebra of all linear operators on V to the tensor power k coincides with the centralizer of the GL and C action. And this phenomenon, when we have two algebras, each acting as decentralizer at the other, we can speak about the double centralizer property. So the centralizer of the centralizer coincides with the original action. This theorem is due to Schur, and it was popularized by Hermann Weyl in his book The Classical Groups, Their Invariants and Representations. There is also a monoid version of this theorem. We can replace the group GL and C by the monoid of all n times n complex matrices. Then both V and V to the tensor power k are still modules, but now over this monoid. And we have a similar statement, that the actions of this matrix monoid and Sk on V to the tensor power k commutes. The monoid generates the centralizer of the Sk action, and Sk generates the centralizer of the monoid action. Let us note that the group of all invertible matrices is dense in all n times n matrices, so both in the Euclidean topology and in Zariski topology, and so in fact it is enough to prove this latter version of the theorem, and the first theorem follows directly. Now here is a sketch of the proof. To start with, the fact that the two actions commute, this follows directly from the definitions. Indeed, one of the actions is component-wise, and the other action permutes components. So of course, acting component-wise and then permuting is the same as first permuting and then acting component-wise. Next, since the symmetric group Sk is a finite group, and we work over the complex numbers, by Maschke's theorem, the finite-dimensional Sk module V to the tensor power k is semi-simple. We can decompose this module into its isotypic components. Then, since the action of the matrices centralizes the action of Sk, it should preserve each of these isotypic components. We can write these isotypic components in the form q lambda tensor over the complex numbers s lambda, where lambda is a partition of k. So here s lambda is a Specht sk module. So these are exactly Specht modules, are exactly the simple modules over the symmetric groups. And q lambda denotes the multiplicity space. And we can show that the image of the metric semigroup generates the endomorphism algebra over the complex numbers of this multiplicity space q lambda, and this implies that the image of our monoid generates the whole centralizer of the sk action. And finally, we observe for the double centralizer, we observe that the image of sk in the endomorphism algebra over the complex numbers of the Specht module coincides with the latter algebra. That's because of the classification of simple finite-dimensional algebras over the complex numbers. Schur-Weyl duality admits various generalizations. In fact, we can view our original vector space V, which is c to the power n, as a natural module over several other groups. For example, we can look at the group of all orthogonal transformations of V, or the group of all symplectic transformations of V, this in the case when n is an even number, so we fix a symplectic form and we look at transformations which preserve it. Or we can actually look at the symmetric group Sn. And there is a corresponding Schur-Weyl duality in each of these cases. Since for these generalizations the action of GLN becomes smaller, so the object which acts on V becomes smaller. So this means that the action on the other side should become bigger, and so on the other side the symmetric group Sk should be enlarged by other elements. So in the case of the orthogonal or symplectic groups on the first side, Sk should be enlarged to the so-called Brouwer algebra, and in the case of the symmetric group on the first side, Sk should be enlarged to the so-called partition algebra. In this lecture we will focus on yet another generalization of the classical Schur-Weyl duality, where on both sides we have algebras of inverse monoids. So in fact we can view our module V as a natural module over the symmetric inverse monoid ISN. Then V to the tensor power k is also an ISN module via the diagonal action. So A acts on the tensor V1, tensor V2 and so on by acting on each component. Note that here we might have that A applied to Vi is 0 because A is an element of the symmetric inverse semigroup. So if some I is not in the domain of A, then A applied to Vi will be 0. And now we want to define what acts on the other side. Of course, the action on the other side will contain the image of the symmetric group Sk, but we will have to enlarge it in some way. So we define the dual symmetric inverse monoid. Let n be a positive integer, and consider the set n underlined, which consists of the elements 1, 2, 3 and so on, all the way up to n. Denote by I star sub n the set of all possible bijections between all possible quotient sets of n underlined. This means that an element of our In star is given by the following datum. We have an equivalence relation xi on n underlined, we have an equivalence relation eta on n underlined, and we have a bijection sigma between the equivalence classes of xi and the equivalence classes of eta. Note that for this to make sense, of course, xi and eta should have the same number of equivalence classes. In fact, the set I star sub n can be turned into a monoid with respect to an operation which we will describe on the next slide. And this monoid is called the dual symmetric inverse monoid. So for the symmetric inverse monoid, elements of the symmetric inverse monoid are bijections between subsets of n underlined. Elements of the dual symmetric inverse monoid are bijections between quotient sets of n underlined. We will represent elements of the dual symmetric inverse monoid using certain diagrams. So if we have an element xi eta sigma, so xi and eta are equivalence relations on n underlined, and sigma is a bijection between the equivalence classes of these two relations. So we will associate to it an equivalence relation phi with the index xi eta sigma. This will be an equivalence relation now on n underlined, this joint union with a primed copy of n underlined. So with a set 1 prime, 2 prime, and so on, n prime. And we define this equivalence relation as follows. First of all, we consider eta as an equivalence relation on the primed copy under the map which sends I to I primed for any I in n underlined. And then we unite the equivalence classes of xi on n underlined with the equivalence classes of eta on n prime underlined under the correspondence provided by sigma. So this means the following. Here is an example. If n is equal to 4, let xi have 3 equivalence classes, 1, 2, 3, and 4. Assume that eta also has 3 equivalence classes, now 1, 2, 3, and 4. And assume that sigma sends the class 1, 2 of xi to the class 4 of eta, the class 3 of xi to the class 1 of eta, and the class 4 of xi to the class 2, 3 of eta. Then our equivalence relation phi with the index xi eta sigma will consist of the following 3 equivalence classes. The class 1, 2, and 4 prime. It is obtained from 1, 2 for xi and 4 for eta. The class 3 and 1 prime, 3 from xi and 1 prime from eta. And 4, 2 prime, 3 prime, 4 from xi, and 2 prime and 3 prime from eta. And we can draw this as the following diagram. So we write elements of n underlined on the top, in the top row of the diagram, and elements 1 prime, 2 prime, and so on in the bottom row. And we connect everything which belongs to the same equivalence class. So we have class 1, 2, 4 prime, it's connected here. We have class 3 and 1 prime connected, and the class 4, 2 prime, and 3 prime all connected. Now we can define our semigroup operation on I star sub n. So let us now explain how to construct the product of the element xi eta sigma after the element xi tilde eta tilde sigma tilde. So these are two elements in I star sub n. For this, we take the corresponding diagrams or equivalence relations capital phi with the index xi eta sigma and capital phi with the index xi tilde eta tilde sigma tilde. We look at the first one, so capital phi xi eta sigma. For each element I in an underlined, we replace I prime by I2 prime in this relation, and then each I by I prime. And let's call the outcome by phi hat xi eta sigma. Now we can consider the minimal equivalence relation omega on the set 1, 1 prime, 1, 2 primes, 2, 2 prime, 2, 2 primes, and so on, that contains all blocks of phi, xi tilde, eta tilde, sigma tilde, and all blocks of phi hat for xi, eta, and sigma. Next, we denote by omega hat the restriction of omega to the set 1, 1, 2 primes, 2, 2, 2 primes, and so on. And finally, in omega hat, we replace every 2 primed number by single primed number. And the output is exactly the diagram for the composition of xi eta sigma after xi tilde eta tilde sigma tilde. Let's look at example. So let us compute phi after psi, where phi is the diagram which we saw before. So the classes are 1, 2, and 4 prime, 3 and 1 prime, and 4 and 2 prime, 3 prime. And psi has classes 1, 1 prime, 2, 2 prime, and then 3, 4, 3 prime, 4 prime. On the intermediate step, we shift phi, so all primed elements become 2 primed, and all non-primed elements become single primed. And then we unite these single primed elements with single primed elements of psi, and we can draw it in such a complicated intermediate diagram. And then we see how in this diagram we get equivalence classes for the equivalence relation on the union of all these things. And then we just remove the intermediate layer and make 2 primed elements 1 primed. That's an outcome, that's phi after psi. It has 2 classes. The first class is 1, 2, and 4 prime. And the second class is 3, 4, 1 prime, 2 prime, and 3 prime. So these are the 2 connected components on this intermediate picture. Okay. This gives us an inverse monoid. So the first basic property of I n star is that this is an inverse monoid. The identity of this monoid is an element equality identity. So equality is the equality relation on n underlined, and identity is an identity map between the equivalence classes of this relation to itself. The inverse of an element psi eta sigma is eta psi sigma inverse. And for diagrams, taking inverse means swapping the top and the bottom rows. The idempotents in this inverse monoid are elements psi identity on psi. That is, they are in bijection with equivalence relations on n underlined. And the product of 2 idempotents corresponds to taking the minimal equivalence relation containing both factors. Clearly, this is a commutative operation. So in particular, the idempotents here commute, which shows that that's an inverse monoid. 2-sided cells, so J cells in this monoid, are indexed by the number of equivalence classes of an equivalence relation, and that's a positive integer between 1 and n. And the maximal subgroups are all isomorphic to symmetric groups. So if we fix the number of equivalence classes, if we fix a 2-sided cell, let's say the number of equivalence classes is I, then all maximal subgroups there are isomorphic to Si. Now we want to define how this monoid acts on V to the tensor power k. For this, consider the standard basis E1, E2, and so on En of V. This basis induces a standard basis on V to the tensor power k, which consists of all vectors of the form E sub I1, tensor E sub I2, tensor, and so on, where all ij's are in n underlined. We can now define an action of the element psi eta sigma in I star sub k on the basis element as above. For the outcome of this action to be non-zero, we need that the following condition is satisfied. For any pair of elements A and B in n underlined, the fact that A, B belongs to psi must imply that the indices I sub A and I sub B in this expression coincide. If this condition is satisfied, then the outcome of the action of our element psi eta sigma in I star sub k on this basis element in V tensor to the power k will be the unique basis element E sub R1, tensor E sub R2, tensor, and so on, which satisfies the condition that for any A in n underlined and any B in sigma inverse of A prime overlined, so A prime overlined is the equivalence class of eta, which contains A prime. The indices R sub A and I sub B must coincide. Let's look at an example. For example, consider the following element psi eta sigma in I star sub 4, which we saw before. It has 3 classes, 1, 2, 4 prime, 3, 1 prime, and 4, 2 prime, 3 prime. Let n be equal to 2. If we apply this element to the standard basis element v1 tensor v2 tensor v1 tensor v2, the outcome will be 0, because in our element in I star sub 4, 1 and 2 belong to the same class. So for the outcome to be non-zero, the indices of the first component and the second component should be the same, but they're different. So we have v1 and v2, so the outcome is 0. On the other hand, if we take an element v1, v1, v2, v2, v1 tensor v1 tensor v2 tensor v2, and apply to this element our diagram, we get the element v2 tensor v2 tensor v2 tensor v1. And we can see this from the following picture. So if we plug in v1, v1, v2, v2 in our diagram, then the bottom row should output the same indices if the two rows are connected. So we will have v2 here because of this v2, then v2 and v2 here because of this v2, and v1 here because of these v1s. Before we formulate the main result, let's look at the following lemma. First of all, the above definition defines an action of I star sub k on v to the tensor power k. Moreover, the actions of ISN and I star sub k on v to the tensor power k commute. Proof. The fact that the above defines an action of I star sub k on v to the tensor power k follows directly from the definitions. If we look how the operation in I star sub k is defined, we see that this corresponds to the definition of the action. To see that the two actions commute, we note that ISN acts on the standard basis either as 0, so if some index is not in the domain of an element, or by a simultaneous bijective transformation of the indices of the factors. And the action of I star sub k is defined using the property that indices inside the same equivalence class coincide. And of course, this commutes with the definition of the ISN action. Now we can formulate the main theorem for this lecture. So theorem, we have claim 1. The actions of ISN and I star sub k on v to the tensor power k commute. The image of the semigroup algebra of ISN in the algebra of all linear operators on v to the tensor power k coincides with the centralizer of the I star sub k action. And the image of the semigroup algebra of I star sub k in the algebra of all linear operators on v to the tensor power k coincides with the centralizer of ISN action. So this was proved in my paper joint with Ganna Kudryavtseva, which was called Schur-Weyl dualities for symmetric inverse semigroup, and which appeared in 2008. Here's an idea of proof. So we already discussed why the two actions commute. And for other statements, note that both ISN and I star sub k are finite inverse semigroups, and we know that the corresponding semigroup algebras are semi-simple. And this simplifies the double centralizer. It's enough to prove that one of them is the full centralizer of the other. The semigroup algebra of I star sub k is a subalgebra of the partition algebra, and so one can use the Schur-Weyl duality between the symmetric group and the partition algebra. ISN is generated by the symmetric group and one more element. That's the identity on the set n-1 underlined. And since we have the explicit formula for all actions, we can see that the extra condition that an element of a partition algebra must commute with an action of this additional idempotent, it explicitly describes the subalgebra of the partition algebra, which coincides with the image of the semigroup algebra of I star sub k. Let's look at one example. Consider the case when n is equal to k is equal to 2. The semigroup IS2 has 7 elements. We have the symmetric group S2 with 2 elements E and transposition S. E is the identity. We have the 0 element 0, the nowhere defined map. And we have 4 elements tau ij of rank 1. I and j are elements in 1 and 2, I is a domain and j is a codomain. The semigroup I star sub 2 has 3 elements. We have the symmetric group S2, E and S, and then I star sub 2 has a 0 element, 0, and that's a unique bijection between the singleton class of the full relation on 1, 2. The space V, in our case is C to the power 2, has standard bases E1 and E2, and so its tensor square has standard bases E1 tensor E1, E1 tensor E2, E2 tensor E1, and E2 tensor E2. So the element S, the simple transposition of IS2, that's in the symmetric group S2, and the element tau11 of IS2 act in this basis of V to the tensor power 2 as the following matrices. So the transposition S of 1 and 2, of course, swaps E1 tensor E1 and E2 tensor E2, and it swaps E1 tensor E2 and E2 tensor E1. So we have the matrix where the opposite diagonal is 1 and the rest is 0. Tau11 sends 1 to 1 and is not defined on 2. So tau11 sends E1 tensor E1 to E1 tensor E1 and is 0 everywhere else. And now if we take these two matrices and compute invariant subspaces, we will see that we have 3 invariant subspaces which do not have any non-trivial invariant subspaces. We have the linear spans of E1 tensor E2 plus E2 tensor E1, and here S acts with eigenvalue 1. We have the linear span of E1 tensor E2 minus E2 tensor E1, and here S acts with the eigenvalue minus 1. And then we have the linear span of E1 tensor E1 and E2 tensor E2. That's a 2-dimensional. So we have 3 simple IS2 submodules of V to the tensor power 2, and these 3 submodules are pairwise non-isomorphic. One is 2-dimensional, 2 are 1-dimensionals, and on these 2 1-dimensionals S have different eigenvalues. This means that the dimension of the centralizer of the IS2 action on V to the tensor power 2 is 3. At the same time, the elements S and 0 of I star 2 act on V to the tensor power 2 as the following matrices. So S preserves E1 tensor E1 and E2 tensor E2 and swaps E1 tensor E2 and E2 tensor E1. And the element 0 of I star 2, it preserves E1 tensor E1 and E2 tensor E2, and it kills E1 tensor E2 and E2 tensor E1. But then if we add to these two matrices the identity matrix, we get 3 linearly independent operators, which means that the action of the semigroup algebra of I star 2 on V to the tensor power 2 is faithful. The image has dimension 3. And so, since the image has dimension 3, it implies that this image coincides with the centralizer of IS2, because we know that that centralizer is 3-dimensional. And as both algebras are semi-simple, the double centralizer follows from a single centralizer. In fact, we can also decompose V to the tensor power 2 as simple modules over I star 2. So we see that both E1 tensor E1 and E2 tensor E2 generate trivial submodules of V to the tensor power 2 of dimension 1. These are trivial submodules over I star sub 2. I star sub 2 preserves both of these vectors. And then we have that E1 tensor E2 plus E2 tensor E1, this should be E1 tensor E2 plus E2 tensor E1. It generates a submodule which is trivial for the action of the symmetric group, but which is killed by the 0 element. And the difference, E1 tensor E2 minus E2 tensor E1, generates a submodule which is a sign module for S2 and is killed by the 0 element. Let us note that the trivial I star 2 module appears with multiplicity 2, and so the centralizer of the corresponding isotypic component must have dimension 4. It should be 2 times 2 matrices over the complex number. So we have 2 modules with multiplicity 1 and 1 module with multiplicity 2. The total dimension of the centralizer should be 6. And this means that the action of IS2 modulo 0 of the complex semigroup algebra of IS2 modulo the 0 element on our v to the tensor power 2 is also faithful, because we have 6 elements there. The dimension is 6. And that's of course the best we could expect, because the 0 element of IS2 kills v, and so it kills any tensor power of v as well. Some additional problems and questions at the end. Problem question 1. Check with all details the associativity of the semigroup operation on I star sub n. Problem question 2. Describe in detail all Green's relations on I star sub n. Problem question 3. Determine the cardinality of I star sub n. Problem question 4. Check with all details that the defined action of I star sub k on v to the tensor power k is indeed an action. And problem question 5. Prove all Schur-Weyl dualities mentioned in the lecture. Thank you very much, and see you next time.